All right, so let's talk about red-black trees. So red-black trees are another attempt to balance a binary tree in some sense. So what's the main reason we want balanced trees when we have binary search trees? Why do we want them to be balanced?
Keeps the order or the searching time low.
Keeps the searching time low, right? If the tree is nice and fluffy up top with not a lot of stragglers down at the bottom, then the search time is roughly log n, right? It's bound by the height of the tree. If you have a million nodes, you can pack it in a tree whose height is about 20. And so a million pieces of data, you can search all of those in 20 operations. But if your tree gets big and long and is a big line, it could be a million nodes in a line. It could take you a million operations to get down to the last piece of data, which is the one you're looking for. So we want to keep the tree's height as low as possible. And so our AVL trees that we already talked about with the rotate operations every time we insert or delete, those are an attempt to keep the tree pretty much uniform height, right? If the depth to every leaf node is roughly the same within plus or minus 1, then you know it's nice and full on top and there's not a lot of extra stuff on one side. So AVL trees, we're trying to normalize the height across all the leaf nodes. Okay, keeps your performance up. Red-black trees have a very different approach. With a red-black tree, we don't have all nodes having similar height. They could be off by 1 million. This node could have a depth of 1 million, this could have a depth of 2 million, and it might still be a valid red-black tree. Okay, so a red-black tree is defined not by some simple criteria like keep the height of every node within 1 of the others, but it's defined by a set of what we're going to call invariants. Okay, these are things that do not change, things that are always true about the tree. So we have 5 invariants. And we'll go through these, but I put this up here so we can refer to it while we're working with these trees on a different sheet of paper. So invariant 1, each node is red or black. Oh, I'm writing secret messages and no one can see. There we go. Thank you. So each node is red or black. And what does that mean? We have a flag inside a node that says, are you red or black? Okay, it could be a single bit, could be something like a Boolean. But some way to code it. So the people who developed this, supposedly they had a red and black marker available when they were working this out. That's why they're red-black trees. But some kind of binary flag to indicate which color you are. So that's invariant 1, that's always got to be true. Property 2, the root is always black. And that's easy, it's just make sure that flag is set to indicate the node is black. Leaf nodes, instead of a leaf node just being a node that has no children, we're going to add nil children to it, okay? Children that are basically null. It's really kind of a programming convenience, and it's not going to change our analysis, but I'm going to put it in here anyway. Leaf nodes have nil children who are black. And that's not going to really be an issue. 4 and 5 are going to be the real things we're going to have to deal with when we start working with these trees. So we're going to talk about these pretty carefully. Property 4 simply says red nodes can only have black children. But we've already got one restriction now on how we can color our nodes. If you just look at 3 and 4, what do those tell you when you combine them? Oh no, it doesn't give us a restriction, never mind.
So far it seems like no nodes.
So far nothing conflicts with anything, right? Just make the root black, and if you have a red node, make the children black, and we're good to go.
Would that mean leaf nodes have to be red
Black nodes can have black children. Black nodes can have red children. Red nodes can only have black children, though. So yeah, the leaf nodes could be either. So here's the interesting one. So let's start with a definition. A node's black depth equals the number of black nodes from the root to that node. So some nodes are black, some nodes are red. For any node, if you pick out the path from the root to that node, and there's always a unique path because there's no cycles, right? So start at the root, there's a unique path that gets you down to any given node. Count the number of black nodes you encounter along that path. That's what we're going to call the node's black depth.
Do we count the root and the node?
Go ahead and count the root and the node. I don't know if the root's officially counted in there or not, but I'm counting it. So it's just measuring the number of nodes, but we only count the black ones. We ignore the red ones in that count. Okay, so property 5 says every leaf has the same black depth. In other words, the path from the root to any leaf in the tree always involves exactly the same number of black nodes. But it could involve a wildly different number of red nodes. So this means that the path from the root to a pair of nodes does not have to have the same number of nodes if we ignore color. This path could be 10 nodes, this path could be 15 nodes. As long as they both have, say, 9 black nodes, this property is satisfied. But if this has 9 black nodes and this has 10 black nodes, we're violating property 5. Everyone clear on that?
So I don't see where red comes in, because if your root is black, and that's all you have is a root, then it would have 2 black children. Where do the red ones come in? Because
They don't have to. You could have a red-black tree that's all black, and it would be a perfectly valid tree.
So if you had the root that's black and has 2 black children, the red comes in where you could also have a red child as well, but it has to have at least 2 black children.
So let's play with some pictures. So tell me what you're describing.
So if you have just the root,
Okay,
it
so
has
root
to
is
have-
black.
that says it has to have 2 leaf nodes that are black children.
If there's no children under here, its children will be black nil nodes.
Okay.
But it could have, a red child here.
And not 2 black children.
But if this is a leaf, it's going to have 2
Oh.
black nil children.
And now its other child isn't black nil anymore.
And this I don't know.
Yeah, so when you added the red, did that get rid of the 2 nil black children of the root?
Yes.
What's the purpose of a red node?
So that's a good question because we haven't really done anything with them yet, right? And this is a perfectly fine red-black tree. It satisfies all those invariants. Here's the idea. Suppose we take 2 leaf nodes, and suppose we look at the black depth of the first node. And suppose, so we pick out this one. Let me pick an agnostic color. Suppose we pick out this node. And let's say its black depth equals n. What is the shortest possible number of nodes from the root to here, ignoring color, if we just count nodes? What's the fewest number of nodes we could have from here to here?
Counting root
3.
Counting the root and the node. Forget the picture, just the black depth is n.
3.
So there's stuff.
Oh,
So up here is the root.
So N.
And we don't know what the colors of anything in here is, but we know that the number of black nodes from here to here is n. What's the shortest possible path from here to here?
And
N, right? So shortest path equals n nodes. Here's the more interesting part. What's the longest possible path from the root to a node whose black depth is n?
2n,
Why?
because you alternate red black.
Because you gotta alternate. So this is gonna turn out to be 2n. And the reason is, we know the root is black. The shortest path is one where every node is black, right? If there's a red node along here, we could take that out and we could find a shorter path, and it would still have the same black depth of n. So the shortest path with black depth n is just a path of n black nodes. So if we want to make a longer path, but we still want the same black depth, we can only add red nodes, right? So where can we add a red node? Well, we can't add it at the root. The root's got to be black. Can we add it as a child of the root? Absolutely. We could put a red node in here. Could we put another red node right here? No, because red nodes have to have black children. So if we put a red node here, the next node's got to be black. But could we make a red node underneath that? Right? Absolutely. But then the next node has to be black. So we can insert, and we could make our last node red as well. So if you have a black depth of n, we could have a total depth of 2n. So what does invariant 5 tell us? It tells us that every path from the root to a leaf node has a total length bounded between some number n and twice that number n.
We wouldn't be able to end it on red, would we?
Sure.
For that specific one, because what that mean one is doing.
So that's that, and then it's got its 2 black nil children, and red nodes need to have black children. That's okay.
If you don't have that, it's 2n minus 1.
Yeah.
So this way you end up having a tree that's perfectly balanced in terms of black nodes.
So it's basically balanced in terms of black nodes. What the red nodes are doing for us is they're letting us define a tree that's not evenly balanced in the AVL tree sense, but still satisfies this property. And because we know the depth to a leaf node is never off by more than a factor of 2 between the shortest and the longest, it puts a bounds on the search time. Okay, it's not log n, but it's 2 log n, worst case. And that's still order of complexity log n. Okay, so this is still preserving our efficient search times. It's still making it order log n. But this is a much more forgiving condition. So having the red nodes in here allows us to make the tree look sloppier, which means it's probably going to take less work to maintain it, right? It's not every time it's a little off, we got to get in there and we got to balance it up and rotate and all this, right? It can get really kind of heavy on one side or the other, but still have this log n search time. So it's a more forgiving version of an AVL tree. Now it's still a binary search tree, okay? Everything to the left of a node is smaller, everything to the right is bigger. We're going to come back to that in a bit. But our constraints on the height of subtrees is just much more relaxed.
So how do you decide when adding a node if it's going to be black or red?
So that's the next part, is how do we use this? What's our algorithm? So inserting into a red-black tree. All right, so we're going to use the usual insert. Okay, so usual operations, which is to add the new node N onto a leaf. So start the root, move down, keep going until you can't go any further, and then put it to either the left or the right of the leaf node that you ended at. Right, so we'll replace the nil child with this new node N, and we'll give N to nil children. Okay, so we insert this new node, and we color N red. So we always insert a red node. All right, and now we have to look at possibilities where we could have violated our 5 invariants, any of our 5 invariants. So we have 5 cases. Case 1, N is the root. In other words, our tree was empty, and we just inserted the first node into our tree. If that's the case, have we violated any of our invariants?
Yeah.
Yes. We violated invariant 2. The root is supposed to be black. What do we do about that?
Change the flag.
Just repaint it. Color it black and we're done. Yes, exactly. Well, someone must have done that. I'm glad you did. So if it's the first node we're inserting, it's easy. Just color it black. We're done. Okay. Case 2, if N is not the root, N has a parent. Because every node except the root has a parent. Now suppose the parent is black. What have we got? We've got a new node that we've just inserted.
It's red.
We had a parent node. Our new node is red. The parent is black. And we've got some subtrees under here. And nothing above here has changed, right? We're only interested, I mean, so we haven't changed any nodes to be anything other than red or black, so 1's fine. We haven't touched the root, because N's not the root, and we haven't changed the parent happens to be black, so 2 is fine. We haven't done anything with leaf nodes, so that's fine. Red nodes only have black children. We added a red node here. Is that a problem?
No. If the parent was red, then you'd want to change the node to black, right?
Mm-hmm.
So the parent's root doesn't have to have 2.
Black and red children.
And as a parent is black, so why is that not a problem?
You
Oh,
want-
because it's a leaf node. So it's got nil black children, so that's fine. And we haven't changed the color of this. And what about the black depth?
There's only one.
There's only one new node, which is here, and its black depth is the same as,
It's parent.
So, yeah, which red node is the only black one?
right? So whatever path we had from the root going to a node through here, right? The number of black nodes going to this node has not changed, right? Because we added a red node. So this is going to be fine. Right, that's an easy case. The other cases get more difficult. And these other cases involve where the parent is red. So we're inserting a node, we painted red, and we look at your parent node, and if your parent is also red, we have a problem. Because a red node can only have black children, and we just inserted a new node whose parent is red, but the node we inserted is also red. So there's a potential issue. And we're going to break these three cases out separately. And they're going to be based on the nature of your uncle. So let's draw our tree. So we're going to have our new node. We're going to have a parent node. We're going to have a grandparent node, and we're going to have an uncle node. Okay, so case 3, and just to be clear, let me go back to my blue code. Just to be clear, N is red, P is red, and in case 3, your uncle is also red. Not red, red. Okay, so you're red, you're red, you're red. And these were red to begin with, now we just added a new red node. Okay, so this is a problem here, right? Okay, do we know anything about the grandparents' color?
Black,
Black, why?
because children are red.
Because the children are red. If this was red, the children would have to be black. All right, so you know the grandparent is black. And we've got some subtrees under here. So we're going to modify this tree as follows.
1 and 2 have to be nil, right? We can just add them in.
Yeah, but we're going to recurse in a moment, so we'll just leave them 1 and 2 for now. But yes, you're right. So we're going to change this into the following. I'll keep using that. But we're going to repaint. So our node is still going to be red. Our parent's going to switch to black. Our uncle's going to switch to black. And we're going to change our grandparent to red.
Doesn't that violate 2?
This is not necessarily the root.
But it could be,
It could be.
and it would violate it.
But for now, let's not worry about it. Let's come back to that in a moment. But let's look at the other ones first. Each node is still red or black. Leaf nodes, yeah, that's no problem. Red nodes have only black children. That's fine. That's fine. Property 5, all leaf nodes have identical black depth. So this one we have to check pretty carefully. So over here, the black depth to G, right, plus the number of black nodes from here down to something in, say, 4 or 5, right, that gives us the black depth of 4 or 5. If we take a path from the root to, say, something in subtree 5, and it goes through G, well, when we take that root in this modified tree, when we hit G, it's not going to increase our black depth, right, because this is red, so our black depth is down by 1. But to get to 5, we're going to have to go through the uncle, and the uncle is now black instead of red. That's going to bump up our black depth by 1. So the total number of black nodes is going to be unchanged, right? Instead of hitting a black and a red, we're hitting a red and a black. And the same thing for any leaf in subtree 4. And for any leaf in subtree 3, instead of going black-red, we're doing red-black. So it's the same number of black nodes, and the same for 1 or 2. So our black depth is identical everywhere. So all of these are satisfied, except possibly number 2, the root is supposed to be black. Well, if G is the root and it's supposed to be black, we can just repaint it. So that's easy, but there's one other possibility where we could be going wrong. And that is G, if it has a parent, if it's not the root, what if that parent is red? So if G's parent is red, then we're going to be violating property 4 right here. So what do you do in that case? We recurse. We're back to the situation where we've added a red node, right? We treat this as our new node, saying that it's red, and this could be a problem. And so we go back and we go through our 5 cases again, and we keep doing that until either the grandparent's parent is not red, or the grandparent has no parent, in which case it's the root, in which case you just paint it black. So this case 3 is recursive, but it's going up through the tree each time we recurse, and we know the height of the tree is bounded by log n, and so the maximum number of times you're going to have to recurse is order log n. And these operations themselves of doing these repaintings, that's order 1. It's a fixed amount of work. So the total amount of work to do this adjustment after you insert is still log n. Right? And the insert itself is log n because you have to traverse down and find a leaf node to tack onto. So the whole thing is still log n. So our performance is still preserved. Okay, questions, concerns about that? This is weird, all right? And you're not responsible for coding this up in assembly language on the exam. But it's a kind of different style of going after a goal, which is why I think it's an interesting case study. All right, so case 3, you insert a red child, your parent was red, and your uncle was red. And we've completely dealt with that. So case 4, n is red, parent is red, but your uncle is black. I think we answered the question while you were gone. What are the red nodes for? The red nodes are basically so you can make the tree conventionally unbalanced. You can add red nodes and have some mismatches in there, but still have it be balanced according to the notion of a red-black tree, right? And when you insert a node, you always paint it red initially. So you're putting in red nodes, and it makes it easier to maintain the balance. All right, so case 4 is where your uncle is black, and case 5 will also handle where your uncle is black. Okay, and those will be the only possibilities. So either you've got a root, no parent, or you have a parent, but the parent's black, or your parent's red and your uncle's red, or your parent's red and your uncle is black. And we break out this black uncle into 2 subcases. Okay, case 4 and case 5. So case 4 is relatively simple. Oh, and before we do that, let's be mindful of the search order. So the search order clearly has not been perturbed here by just changing the coloring of these things, right? It's still going to be 1N2 P3 G 4U5, right? And it's exactly the same order over here because we haven't moved any nodes data around. Okay, we've just changed colors. But we're going to start moving data in cases 4 and 5. All right, so case 4, you've got an uncle and the uncle is black, and I'm going to draw it as follows. So case 4 is going to be, here's your node that you just inserted. Here's your parent. Here's your grandparent, here's your uncle, here's some subtrees. And case 4, the new node you inserted is red, your parent is red, your uncle is black, and your grandparent has to be black because it has a red child. And we're just going to redraw this slightly differently. So we're going to turn this into, move the parent down here, move the new node up there, grandparent, uncle. Carry these subtrees along like this. This is red, this is red. This is black, this is black. All we've done is switch around the parent and the new node, and we've mirrored it. We flipped it from being on the right side to being on the left side. Okay, so case 4 is specifically this case where your uncle is black, your parent is red, but you're sitting as the right child of your parent. And in that case, we do this modification, which now makes the parent the left child of you. But this is going to be case 5. And we're going to pretend that this is the node we just inserted and this was the parent. When we talk about node and parent, N and P in case 5, right, we would treat this as N and we would treat this as P. And case 5 is going to be the case where the new node is to the left of its parent. So we haven't changed the colors, right? But we want to check the search order as usual. So what's the traversal order, left node right, in order traversal? Starting from here, we would traverse subtree 1, and then the root, and then we traverse the right subtree, which will be 2 and 3. That's the left subtree traversal, then we hit the root of this tree, and then we traverse the right subtree, which is 4u5. Over here, traversal order, well, first we traverse this tree, which means traverse this subtree, so this is 1P2, and then traverse the root, and then the right subtree 3, that's the whole left subtree, then traverse the root, and then traverse this right, U45, so left subtree, root, right subtree, 1P2N, 3G4U5, same search order. So we haven't stopped it from being a binary search tree, which is important. All we've done is transform this into a case that we can treat as case 5. So in our code, we need to rename this node as N and this node as P, and now it looks like case 5. So case 5. N is red, P is red, U is black. So in this case, we look like that. In this case, we look like this.
Oh, so if it's 4, then you make it to where it's
You
going to
make
be
it into 5,
Okay.
yeah. And along the way, we have to do this rename operation where we call this N and we call this P. And now this looks exactly like case 5. We're almost there.
You said you switched the name of N, P and N.
Yeah, because after we swap P and N and we move to the other side, right, this was actually our parent, this was actually the new node. But that doesn't really matter for what we're doing. We need an algorithm, and our algorithm uses N for the node that's the child of the node above it, P. So in our code, we'd call this N and we'd call that P. Is this like anything you've ever coded recently? Right, this is just really freaky code. And we'll We'll talk about that in a minute. All right, so here's case 5. You got your new node, you got your parent, you got your grandparent, your uncle, we've got subtrees. And what have we got? The new node is red, the parent is red, and the grandparent and uncle are black. Right, and our whole goal here is to maintain these invariants, and the big issue right now is this red parent, right? If the parent's black, that's case 1 or 2. So this is the issue with the parent being red, because you can't have red with black children.
Just
So we're-
change it in black and you're good.
Yeah, just don't tell someone to look the other way. So we're going to change this into the following. N and P. P's child is going to be the grandparent, and the grandparent's child is still going to be the uncle. And we're still going to have subtrees here. 1, 2, 3, 4, 5. And we're going to color as follows. Our new node's going to be red. The grandparent's going to become red. The uncle will stay black. And the parent will be black. Okay, let's check traversal order first. 1, N, 2, P, 3, G, 4, U, 5. 1, N, 2, P, 3, G, 4, U, 5. Same search order. We're so good on that count. Red nodes have only black children. So there's a red node, black children. 3 must have been black, because it was, the root of 3 was the child of P, which was red, so the root of 3 must be black, so that's satisfied, and same for 1 and 2. So the black depth is the interesting question, right? Do all nodes still have the same black depth? And if we're getting to a leaf node in subtree 1, so here's our original tree, right, before we added in N, and we had a certain number of black nodes to get to G, and then we went through a red node, and then we went through, N didn't exist, but it's red, and then we got down into subtree 1, we had a certain number of black nodes, and a path from the root to that node in 1 is still going to go through one black node, right? It happens to be the parent, but it's black. The child of that parent is red now, nothing's changed. And the same with 2, we used to go through a black, and then a red, and same thing here, we go through a black and a red. And for 3, we'd go through a black node here, and then just reds. Here we go through black and reds. And for 4 and 5, we go through 2 black nodes, and then into the subtrees, and that's still the case. So the black depth of all the nodes in these subtrees has been unchanged by this operation. So this satisfies all the invariants, and we're good to go. So what does this all mean? We have this primary goal of trying to insert into a tree while maintaining a good search time, right? Maintaining an order 2. With an AVL tree, we do that by forcing the heights to stay within one of each other, which we do by these rotates and stuff, balance factors. With a red-black tree, we develop a set of properties and say as long as all of these properties are true, we have good search time. And now we completely forget about that initial goal. Nowhere in here did we analyze the depth of the tree or the balance factor of the nodes or anything like that. We're just working to maintain these 5 properties, having confidence that if we maintain these, then our search time is order log n. So when we insert a node, all our focus is on these, right? It's a redirection of your goal space. And this happens sometimes in programming. We're trying to accomplish some task, but we develop some other version of a task and say if we can do this, that gets taken care of. And now our code is all about working on this thing. Is this a good place for comments? Probably. Because you come back to your code where you're balancing a tree and you start doing this kind of stuff, you're not going to have any idea what you're doing. Right? And it's not just because red-black trees are crazy, right? It's because the goal space is totally different here, right? Nothing directly to do with balance factors or heights of trees. It's buried inside here and here, this bound on path difference, path length difference. But we don't really think about that when we're coding this up, right? So we've got a new set of goals that we're working on that's going to serve us in the end, right? So these are interesting types of programs to work on because they sort of force you to get a little more abstract in your thinking. And for me, I find it very comfortable when I'm writing a piece of code if I have in my mind all the time exactly what I'm trying to do, right? And almost every character I type, I know how that's contributing to the goal. And this kind of thing, that's really hard to do, right? Because your goal is somewhere down there, right? And I'm just trying to do this thing over here. So that can be good practice to work with. Yeah.
I found a good visualization for red-black trees.
Oh,
actually.
cool.
Yeah, just literally Google red-black visualization,
Yeah,
and
it's
it goes
really
through all
cool.
the steps of adding numbers.
Yeah,
Oh, let's do
slowly
that.
adds a bubble
Yeah.
and then puts it in,
really
does
cool.
its little thing.
Yeah, the very first one.
Is there music?
Yeah, there is.
Cool.
Human music.
You can always make music.
All right, so there's a 5.
You know it'll be black.
Let's do a 7. Cool. All right, let's just do a horribly linear one and see how it does it. Cool.
You can also slow down animation.
Yeah, let's do that. Cool. So this is pretty clearly not balanced now in the classic sense, right? The left subtree has a single node and the right subtree has 3 nodes from root to end, so it's a height of 0 and 2, right? So it's not balanced, but it's a good red-black tree. So let's keep upsetting it. And at some point, we're going to have to get some stuff over on the left, right?
Right here.
Like right here.
So it's not balanced on the right traditionally, but it is balanced because
Yeah.
the black depth is the same.
I was gonna add
There we go. And so that, I believe, is where we're going from this to this, right? Because this basically has stuff that's sitting on the right, and we turn it around and put it on the other side. And I think that's what we're seeing there. And the same thing if it's the other way around. That's cool. I like that. They should have an automatic one that just like throws in random data though. Because that would be pretty sweet.
You have a sign for next to
There you go. Yeah. PA6.
use a
In a
GUI
clips.
to make it black.
Yeah.
So then they have a PA6 that's gonna be rough.
Yeah. What?
What would deleting look like? Would that replace
Oh, let's
what we
delete.
just did?
Should we delete the root?
Oh yeah.
Oh yeah.
You have to watch it break.
Oh, that's okay.
Algorithm in the last place.
Yeah. So let's make it lopsided. Well, let's put something back in. Oh, let's delete from the left side. Alright, so let's take out that 7. And then let's take out the 5. Oh,
Deleted
The heck?
too.
I didn't mean it.
I didn't mean to come back.
Maybe delete doesn't work. Maybe it's all a ruse. All right. Well, I was going to delete the 5 on the left, and then it would be really lopsided, and it would have to somehow rebalance. But play with that at home.
That's at least
The
minus
tree was
five
too
dollars.
loud.
Yeah, yeah.
All over.
So rule number 3 is just for ease of coding it.
Yeah, so it takes care of things like when you have a red leaf node, right? It's automatically got 2 black children, which are nil. Otherwise, you have to put special cases in here, like red nodes have black children unless they're leaves or something like that. I think that's the main reason.
Okay.
All right, questions, comments? You want to code this up?
ODP.
Yeah, that'll be an ODP.
With the GUI.
Yeah.
You have to recreate that.
All right, so we talked about trees. All right, so next week we will go through regular expressions and Huffman encoding. Huffman encoding is a compression scheme you can use to compress something like text to make it take fewer bytes to store, but it's lossless. So you get the ability to completely restore the original version of your data. So we'll do Huffman coding, and we'll touch on regular expressions, and then we'll probably be ready to go on to PA5, so which is due next Friday. PA4 is due next Friday, so we'll do PA5 on Wednesday.
Next Friday as well as PA4.
PA5, so we talk about the PAs the Wednesday before the previous ones due, right? Because we don't meet on Friday. So Wednesday we'll talk about PA5, Friday PA4 will be due. We don't meet on Monday. Oh yeah, man, we get double whammied. All right, so yeah.
For the lab 4, are we supposed to connect the one directly to the breadboard?
Connect to the breadboard, just because it doesn't make a really, really great connection, and it'll wiggle around less if it's on the breadboard, because you put all 4 feet in. Yeah. Or if the button's giving you trouble, you can test it just by taking the 2 wires and touching them together. That works fine. Yeah. All right, so I will not see you on Monday, so I will see you on Wednesday, or I'll see you in office and stuff before then.